Hello, welcome to the NPTEL course Fundamentals of Composite and Cellular Materials. The topic for today's lecture is dependence of properties on pore structure and pore morphology. We already learnt so far that for porous or cellular materials, the porosity is a very important factor, and we need to find out the pore morphologies, the porosity and its amount and distribution very accurately. In the last lectures, we learned 6 different techniques which can actually give porosity with different amount of accuracy. We learned about the techniques like bulk density analysis, density from Archimedes principle, porosity from mercury intrusion porosimetry, PPI technique, and also image analysis and computer tomography. And in this lecture, we will learn that how this porosity and its distribution and morphology actually affects the properties of the materials. Now, this knowledge is extremely important to actually model and develop the porous materials, because for porous materials development, it is extremely important to know that how the pores are actually affecting the properties of the materials. So, today's lecture will be divided into 4 different sections. In the first part, I briefly discuss about the dependence of the properties on porosity of the materials, and then I will briefly introduce about 3 different modeling approaches: the earlier models, then the Gibson and Ashby model, and the minimum solid area models. In the next lectures, we will learn in much more detail about 2 modeling approaches which are very commonly used for porous materials, the third and the second one, that means the minimum solid area approach and the Gibson and Ashby model approach. The main keywords for this lecture are mechanical properties, modeling, then Gibson and Ashby model, cell interconnections, and minimum solid area models. Now, in terms of the dependence of properties on porosity, the properties can be classified into 3 different groups. There are properties in the first group which do not depend upon the porosity at all. Then there are properties of the second group which depend only on the amount of porosity, with the pore character, that means the pore shape, its morphology, its size and so on, they play no role. And in the third group, we have the properties which depend both upon the porosity and the pore morphology. Again, these include whether the pores are open or closed pores, the shapes of the pores, the size of the pores, their anisotropy and so on. So, as is being shown in this slide, the properties can be classified again into 3 different groups. The properties like theoretical density and melting and boiling point are the properties which do not depend upon the amount of porosity. That means, even if you have a porous metal, it will still melt at the same melting point as the bulk metal. Also, the theoretical density of the material will not change. That means, the density of the bulk of the bulk material inside the cellular solid, that means the solid struts and the faces, they will still be the same as the bulk metal or the ceramic of which the porous material is made of. In the second group, where we have properties which depend only on the amount of porosity, they are the properties like the volumetric specific heat or the Curie temperature. That means, these properties they depend upon the porosity, but here the pore shape and its distribution or morphology, they play no role. It is only the amount of the pores which is the most important case. And for the third scenario, where the properties depend upon both the porosity and pore characteristics, and most of the mechanical and thermal properties actually fall in this category. And here again we can actually have 3 different subdivisions. In subdivision A, where the flux or stress transmission is only through the solid, that means, if you just assume that you have a porous material, that means the porous material is what? You have a solid struts or faces which are kind of separated by the air content inside the struts and the faces. So, the properties of group 3A, they only depend upon the amount of solid, that means, they only the stress or flux transfer, it only happens to the solid phase. Then in 3B group, we have the flux or stress transmission occurring only through the pores inside the sample, that means, it does not happen through the solid. And then in group C, we have where the flux or stress transmission occurs both through the solid and and the pores inside the sample. So, as I mentioned, most of the mechanical properties like the Young's modulus, fracture strength, flexural strength, fracture toughness, and also the thermal properties like thermal conductivity, electrical conductivity, etc., they are the properties of category 3A. That means, for these properties we need to know both the amount of porosity and the porosity distribution. That means, whether the pores are closed or open, how much open, or whether the pores are all spherical or kind of elongated. All this information we need very precisely to find out the dependence of the properties of this kind on the porosity. At the same time, there are, I mean, this transition from the 3A to 3B also, that means there are some properties which also depend upon the pore characteristics. That means, at low amount of porosity, where we have, for example, less amount of pore interconnectivity, or for example, at high temperatures where, for example, the convection also plays a role. In those cases, there are properties which actually convert or kind of transmit from or transit from group 3A to the group 3B. So, that means the basic thing is that we see here that we need to characterize for those properties of group 3, we need to know both the amount of porosity and its distribution and morphology very precisely to find out the dependence on the porosity. Now, as I mentioned, 3 different approaches have actually been carried out to find out the dependence of the properties on the porosities. The first or the initial theorists actually proposed these empirical models, where you see this kind of models were proposed especially for Young's modulus, but these models were subsequently also expanded for strength and other properties. So, especially what we can see over here is that, as I already mentioned, all those properties which suffix 0 are basically the properties of the bulk material. That means, here capital E that we see over, this is the Young's modulus of the porous material, and E0 is the modulus of the bulk material or bulk solid of which the porous material is made, and this rho by rho 0 again it is the amount of, this is the relative density, which is nothing but rho is the density of the porous material and rho 0 is the density of the bulk solid, and n is an empirical constant. That means, we can simply use this expression for finding out that like what is the value of n. That means, by varying the value of n, we can actually fit this expression for experimental data. And these expressions are very simple. I mean, these expressions, there are several expressions have been proposed. As you can see over here, there are many such expressions. Typical expressions for Young's moduli are being shown over here, but there are also many other expressions have been proposed to actually project or kind of predict the dependence of the Young's modulus on the porosity of the material. Again, Young's modulus have been studied very often for porous materials, because it is structure sensitive, and any deviation in the pore size and the pore morphology will actually affect the Young's modulus of the material. So, but this technique or this kind of modeling approach, it has some limitation. So, the main limitation is that this actually assumes a very simplified pore shape or simplified pore dimensions. That means, the real pore shapes and the real pore dimensions are actually not taken care of in this kind of model. Also, these models, as we will see afterward, that these models typically predict this kind of an analysis. That means, if we try to plot the value of the E over E0, which is basically that the modulus of the porous material normalized by the modulus of the bulk material, and as a function of the porosity fraction or the pore fraction along the x axis, we end up with this kind of shapes. That means, these models, one of the biggest drawbacks of these models are that these models actually, or many of those models actually assume that at 100% porosity we actually end up we obtain kind of zero property value, and at lower porosity, that means at 0.6 or 0.7, that means around 60 to 70% porosity, we still have significant amount of the property value. That means, the stiffness of the sample at 60 to 70% porosity is still predicted to be pretty high, whereas in real scenarios it is actually obtained that there is a limit called PC or percolation limit, up to which the properties are kind of finite, and once the porosity actually crosses this PC or percolation limit, there actually a drastic drop in the properties. So, typically if you in real world, if you try to plot the property, you typically end up with this kind of an analysis. That means here this is the porosity and this is your 1 point, that means this is the 100% porosity. That means in real materials it is observed that already at an intermediate value of around 0.6 to 0.7 porosity, you already obtain almost a negligible property value. But these models or these earlier models actually do not consider this kind of a dependence, and they actually predict that you end up with a normal finite value even at a very high amount of porosity. So, these are the main drawbacks for this kind of models, and also we can say that depending upon the amount of porosity we have, there is also a large scatter. That means the range of porosities predicted by these models are pretty high. As you can see that we have a very large range of property values predicted based on a very large based on the amount of porosity, and that is why although these initial empirical models they are still being used and they are also they are useful in predicting the material properties, but when we use these models, we need to practice caution and we need to be careful about the limitations and the disadvantages of these models. The second approach, which is very commonly used and which will also be used extensively in this course, is the modeling approach proposed by Gibson and Ashby. So, these Gibson and Ashby models, which were initially proposed in the late 1990s, and it is also available in the seminal book by the authors. So, in these models actually they put more emphasis on the porous microstructure and the pore morphology, and they actually for different kind of porous materials like honeycombs or open cell foam or closed cell foams, they actually assume simple shapes like this kind of, in this case these cuboid shapes have been proposed, and then actually they use the in these models again the most important parameter is the relative density, means the rho over rho s, and then again they actually try to use this cell dimension, that means the thickness of the cells or that means the thickness of the cells or the length of the cells. These parameters are actually used to find out this rho over rho s, and then these expressions are actually used to find out the properties of the materials as a function of the porosity of the materials. Now, these models they can also be used for properties, not only for elastic properties, as we will see afterward, like when we apply stresses, they can be depending upon the material, whether it is a ceramic material or polymer or metal, the cell walls may undergo buckling, bending or crushing, and Gibson Ashby models have actually proposed equations or simplified relations to actually find out the properties based upon all those parameters. Now, this GA model or the Gibson Ashby model are much closer to the real pore structure in comparison to the empirical models I discussed at the beginning, but again this GA model or the Gibson Ashby model has a big limitation, or the big drawback is that these models typically assume that the pores are, that means it is kind of for cellular solids only, but the truly cellular solids, that means this modeling approach is only valid when we have the this amount of dense material is very less in the material, and these models are valid only for a relative density of less than 0.3. That means only for those materials having more than 70% porosity, only for those materials these Gibson Ashby models have been are truly valid, and these models are actually again these models they actually provide different expressions, and again they have different constants in those expressions typically written as C, and these constants actually propose or differentiate between the honeycombs to open cell foam and the closed cell foams. And as I mentioned, it is only a brief description of the GA model I provide right now, and in the subsequent lectures of this model I will provide a much more detailed analysis of the GA model and how these Gibson Ashby models are actually useful for find out the properties of the cellular solids will be discussed in detail. The third modeling approach which has been very successful and which is very famous is the minimum solid area models or the MSA model. These MSA models, they have, I mean, in comparison to both the earlier approaches, they are much closer to the real property values, and these models actually in comparison to the GA model, these models actually provide they actually are able to predict the material properties over the complete range of porosity from very low porosity to very high porosity. Now again these MSA models, they actually assume a uniform packing of identical cells, as you can see over here. So typical assumption of the MSA model is being shown over here. That means the model starts with one single cell. Again there are two different possibilities are there. One option is there that this cell is basically, the cell is made up of that means these areas, that means these areas are actually made up of a bulk solid, and then we have inside the bulk solid we have a spherical pore, and then the dimensions of the pore and the cell walls, they depend upon the amount of porosity, and then these individual cells can be packed together side by side, and this way the whole complete porous solid is actually built. Other way around, it is also can be there that if for example the pores are much, the pore volume is much higher, we can assume that this solid or the sphere inside the unit cell is actually made up of a solid, and the surrounding unit cell is actually the air or void space. So these two approaches of filling the unit cells have been used in this MSA model, and then this circular region that you can see in each of this thing, these are actually called the minimum solid area. So basically the assumption is that when we pack the individual cells side by side, as is being done over here, so this is this circular area is the region through which the individual spheres inside the individual solids, they actually touch each other. That means this is the region or this is the area over which the adjacent cells touch each other. So this is the concept of the minimum solid area. So basically the basic assumption is that whenever we have stress transfer, for example for mechanical properties or heat or flux transfer for the thermal properties, this transfer actually occurs from one cell to another only between the or only through the minimum solid area contact between the nearby or neighboring cells. So again, I mean, to explain this concept even further, we have seen here that in this slide we see this case A, B and C and D. So case A is, for example, one situation where it is a dense uniform body, and then these arrows are basically showing the direction of your load or flux transfer. So now because now we have a dense body without any discontinuity, so the flux transfer will be uniform over the sample, that means there is no discontinuity, and we have the transfer throughout the sample. But now in case of B, for example, if we assume that there is a plane, and along this plane most of the material has been removed, that means these hatched areas, they actually show the regions or areas where we have pores, and only those regions like these areas are the areas where we have continuity between this side and this side. That means if we are applying some load or flux on this side, the load or flux transfer from this side to this side can only happen through this neck region between the individual pores, which is being shown over here. Again, if we take a more realistic situation where we have, for example, these hatched portions in image C is being are the pores, and in this case these are the solid materials. Again we can see over here that this is the, again we can see that this area or this area over which there is a contact over here, this is the minimum solid area over which the cross section over which the flux or load transfer can actually occur. That means the idea is that once we find out or once these models try to find out the amount of the MS amount of the area over which there is contact between individual cells or neighboring cells, and then dividing this MSA or the minimum solid area value over the complete cross sectional area, and then the material properties can actually be correlated to this minimum solid area value. And this approach has been very successful, and this approach has also been able to also predict not only the mechanical properties, but also other properties like thermal properties, like the fracture strength, and all those things have been very successfully proposed or kind of predicted or kind of by these MSA models. And these MSA models or the minimum solid area models have also been established not only for spherical pores, but also for tubular pore, for cubical pores, and also for other shapes. These MSA models have been established. Now, if we try to find out this the dependence of the minimum solid area or the relative strength of the material as a function of porosity, this MSA model typically predict this kind of a behavior. So, you can see over here this curve or this is typically predicts 3 different regions. So, as you can see up to certain amount of intermediate porosity, we have, like for example, we have a straight line, and then there is a region over which we have a kind of a drop over here, and then we have this critical value like this value over here, which is called the percolation limit, where we have the if the porosity is more than that, then the property values will actually approach the value of 0. So, again we have 3 different regions. In the initial region or the initial point, which is up to around 0.3 to 0.4 porosity, and this region typically has the dependence of e to the power minus Bp. That means, in this case we have like if E is your property and E0 is the bulk material property, then this typically has the relationship of it's proportional to e to the power minus Bp, where P is the amount of porosity. That means, if you simply take semi-log plot, that means if you have take logarithm of both sides, you can simply make log of E over E0, and that will give you your minus Bp, your minus Bp dependence. That means, this initial region where you can actually plot a semi-log plot, that means you plot your property as in a log scale. So, log of E over E0 and the porosity in terms of your linear scale, you typically obtain a curve like this. And this initial portion, this slope, this dependence is basically the value of the B that you obtain from this expression over here. And again this value of this constant B is actually dependent on the pore shape and the pore morphology, and this B actually controls that how strongly the pores are able to reduce the property value. So, you can see over here that in this, for example, in this case the B is 1.4, whereas in this case the B is 9. That means, as you can see that if the value of the B is small, so if you have a low B value, then porosity has lesser or lower influence on the property. That means, for any property or any pore shape for which B is low, that means that with increasing porosity, the drop in the property value will be much lower in that particular case. Whereas, if B is very high, say for example 9 in this case, with increase in porosity, the drop in the property will be much more drastic. So, after this case, after this initial case or after this initial where you have a linear dependence of the semi-log plot, you have another region, this is region 1, this is then region 2, and this is region 3. In region 2, this is called kind of a drop down or kind of a drop down region, where the plot deviates from linearity, but still the rate of drop is not that drastic. That means, it is this particular region over here. So, if I just take, so this particular region over here in this particular curve, where the drop or the rate of drop of the property with increasing porosity is actually increases, but still you obtain a finite value of the particular property. But then this value, this is the starting from this point, and this critical point, which is called the critical or the percolation limit, at this point when we obtain this point, they are actually, even though the 100% porosity is somewhere like here, this is the 1 or 100% porosity, but even at much lower values which can range from around 0.5 to 0.7, 0.8, at such a low value of porosity where you do not expect, following the or in the earlier models which proposed that the property should reach 0 only at 1%, only at 100% porosity, but these MSA models they predict that already at a critical value in the range of 0.5 to 0.7 porosity, already your properties are approaching the 0 value. And also these models have been very successful, because if we try to actually find out the properties of the real porous materials and try to plot them or try to find out the properties over a range of porosities, we actually end up with this kind of a curve, where we also obtain that that above the critical porosity of PC we also obtain a almost 0 property value, and these things will be discussed in much more detail in the coming lectures. So, to conclude today's lecture, we discussed about different ways how properties are dependent upon the porosities. We learned that there are 3 different ways that can be have been typically been used to predict the properties and their dependence on the porosity. The earlier models were mainly empirical models which did not actually consider the pore shapes, and these models were mainly based upon the amount of porosity. But these models were kind of not satisfactory, because they are unable to actually predict the real dependence of the property on porosity, and they also predict that the property will only become 0 only at 100% porosity, while in real materials it is observed that the properties they actually become 0 already at a intermediate value of around 0.6 to 0.7. An improved modeling approach was proposed by Gibson Ashby, who actually used some simplified unit cell type of things, and then using the dimensions of the unit cells, like the thickness of the cell walls or the length of the cell walls, they actually proposed expressions to find out the properties for different kind of cell geometries like honeycombs, open cell forms or closed cell forms. But again this Gibson Ashby model, they have the limitation that these models are again valid for very high amount of porosity, typically for cellular solids with more than 70% porosity. And finally, we discussed about the more accurate minimum solid area models, and these models actually consider the interconnection, the minimum point of contact between 2 unit cells, and these it is assumed that the flux or load transfer actually occurs from one unit cell to the other unit cell only through the minimum area of contact between the unit cells. And these models typically predict 3 different regions in the semi-log plot of property over porosity, and these models are also very accurate because they can actually predict the real dependence of property over porosity, and they also kind of highlight that the properties can actually become 0 at a much lower porosity, much lesser than 1, and which is called the percolation limit. And in the next lectures we will learn in much more detail on real materials where this MSA model has been established, and also we will learn in depth about the various GA models and their applicability for different kind of loading conditions. The references used for this lecture are shown here, and in the next lecture we will study much more about the minimum solid area model and the Gibson Ashby model for various kind of cellular solids, especially for honeycombs will be covered in the next lecture. Thank you very much.